Imagine you're floating in the deepest, darkest corner of intergalactic space. You are adrift, far from any star, any planet, any speck of dust. All around you is the perfect vacuum, the ultimate nothingness. It's an emptiness so profound, so absolute, that it seems to define the very concept of absence. This is the stage upon which the grand cosmic drama unfolds. We've always pictured space as the silent, empty backdrop for the brilliant dance of galaxies and stars. It's the canvas, not the paint. But what if this picture, this fundamental assumption, is completely wrong? What if the void isn't void at all? For centuries, our understanding of the universe was built on this idea of a passive emptiness. How can something come from nothing? It sounds like a paradox, a violation of the most basic rules of existence. Yet, in the quantum world, it happens all the time. The vacuum of space is constantly borrowing energy from the future to create pairs of particles. These are called virtual particles. Imagine the vacuum as a bank. It can grant a tiny short-term loan of energy. With this loan, a pair of particles, one made of matter, one made of antimatter, can burst into existence. They live on borrowed time, and they must pay back the loan almost instantly. They come together and annihilate each other, disappearing back into the nothingness from which they came. This process is happening everywhere, all the time. In the space between your eyes, in the vastness between galaxies. If the vacuum is a boiling sea of virtual particles, then it must contain energy. Even after all the matter, all the radiation, everything we can see is removed from a patch of space, there is a residual energy that remains. This is the energy of the vacuum itself. A baseline energy that can never be reduced to zero. Physicists call this zero-point energy. It's the energy that space-time has simply by virtue of existing. It's the lowest possible energy state of any quantum system, and it is not zero. This inherent energy of nothing has real, measurable consequences that we can observe right here on Earth. In 1948, Hendrik Casimir proposed an experiment to prove vacuum energy was real. He imagined two perfectly smooth, uncharged metal plates placed incredibly close together in a perfect vacuum. Outside the plates, virtual particles of all wavelengths can pop in and out of existence. Between the plates, only virtual particles with specific wavelengths, those that fit into the tiny gap, are allowed. For most of the 20th century, we thought the expansion of the universe was slowing down. After the Big Bang, everything rushed outward. We assumed the mutual gravitational pull of all the galaxies and matter would act like a brake, gradually slowing the cosmic expansion over billions of years. But in 1998, two teams of astronomers studying distant supernovae made a shocking discovery. The expansion of the universe isn't slowing down at all. In fact, it's speeding up. Something is pushing space apart, overpowering the collective gravity of everything in the cosmos. This mysterious something was given a name: dark energy. It appears to be a property of space itself, an anti-gravitational force that stretches the fabric of space-time. The more space there is, the more of this energy there is, and the faster the universe expands. So, we have a beautiful idea. The vacuum energy predicted by quantum mechanics could be the dark energy that's causing the universe to accelerate its expansion. It links the world of the very small with the world of the very large. There's just one problem. When physicists use quantum field theory to calculate the amount of energy that the vacuum should have, they get a number that is astronomically, stupendously, absurdly large. It is a number so big it's hard to even write down. It's a 1 followed by 120 zeros. Trillion, trillion, trillion times larger than what we observe. This discrepancy is, without a doubt, the worst prediction in the history of physics. It has been called the vacuum catastrophe and the cosmological constant problem. It's the biggest mismatch between theory and observation that science has ever known. If the vacuum energy were really as large as our theories predict, its repulsive force would be so immense that it would have ripped the universe apart moments after the Big Bang. Stars would never have had a chance to form. Galaxies would never have had a chance to form. Atoms themselves would have been torn asunder. Clearly, our calculations are missing something fundamental. We live in a universe that is not blown to bits, so the theory must be wrong. Why is the observed value of dark energy so small, yet not quite zero? We started with a simple image: the cold, silent emptiness of space. We end with a profound and unsettling truth. That emptiness is the most active, energetic, and mysterious part of our reality. The vacuum is not a void. It is a plenum. A dynamic stage where the fundamental rules of existence are written and rewritten in every instant. This isn't just a philosophical musing, it is the world described by our best science. It forces us to ask a fundamental question. What does it mean for nothing to be the most powerful something in the universe? It means our intuition about reality is deeply flawed. This journey into the void changes our place in the cosmos. We are not just isolated bits of matter floating in a passive emptiness. We are part of a vibrant, interconnected whole. The same quantum foam that drives the expansion of the universe is also present in the space between the atoms in your own body. The forces that hold you together are mediated by the ghostly dance of virtual particles. We are intrinsically linked to the energy of the void. We are children of the vacuum made of stardust held together by the energy of nothingness. What does it mean for our understanding of reality if nothing is actually something? Share your thoughts in the comments below. If you're fascinated by the hidden depths of the universe, make sure to subscribe and ring that bell for more deep dives into the cosmic enigmas.